Welcome to 3.3, the complete solution to AX is equal to B. Now, before we hop right into it, I kind of have our objectives for this video listed. This is meant to just kind of help remind me, and I'm not sure how visible it is in terms of the phone because of the glare from the windows, etc. But essentially the three main topics for this video are going to be forming an augmented matrix, since we are now setting our equation equal to another vector, something that's not zero. So creating that augmented matrix and putting that into reduced row echelon form. From there, talking about what is a particular solution, how do we find that particular solution, as well as kind of rounding the video out with a quick conversation around full column rank matrices and the types of solutions we can expect from that, taking in our knowledge from 3.2 with the null space, along with and kind of in addition to, quite literally in a way, to solving this when we're trying to find a particular solution. Our system is set not equal to zero, but again, something that contains non-zero entries, and what that kind of looks like. So I'm gonna try to start doing that. I think that'll be a good idea, just as we keep digging into more complex ideas, and it's just good teaching pedagogy, right? Of what are we doing, why are we doing it, to hopefully help, especially the learner. So the example, as far as the textbook goes, that he puts up that I really like is we're looking at this system. And this is really different from what we saw in chapter 2 and chapter 1 when we were solving these kind of systems. Because notice that matrix A does not have to be square invertible matrix. It can be rectangular. So in this kind of case, because when I initially wrote this up, I was just kind of talking to myself, as most brilliant people do. Jokes. Which is this having four components looks kind of funky, but when you really kind of notice again the dimensions and the matrix multiplication here, if matrix A is a 3 by 4 and this is a 4 by 1, when I do this multiplication, we'll be left with a 3 by 1. So just kind of keeping in mind how those dimensions work and how they interact. So again, although it looks kind of weird, this is actually the correct setup. And it's, again, a little bit different from what we've seen in previous units because my matrix A no longer has to be a square matrix. And so when we see something like this, we can start getting into a little bit more interesting dynamics. Most matrices are not square, and systems don't always have to be square. And so what do we do with that? And so if I start with this setup, and this is kind of getting into that very first objective, to ease our solving process, I can actually create a single matrix called an augmented matrix. And what that augmented matrix looks like is this. We essentially create a block matrix where I'm going to take my matrix A, which is 1, 3, 0, 2, 0, 0, 1, 4, 1, 3, 1, 6. And I'm going to use a dotted line. Some textbooks will use a bold line. It's completely up to your personal preference. But the idea is that I attach this vector B onto the end. So we create this augmented, this longer matrix. Yeah, I always want to say matrixy, but this longer matrix. And as we perform elimination here and try to take this matrix and put it into reduced row echelon form, remember that whatever happens to this needs to also happen to this vector. And we saw this again in previous units. And by doing this augment, we can then apply it all at one time. We used this process when we were trying to find the inverse of a matrix. By placing the identity matrix on the right-hand side and creating an augmented block matrix, as I go through and perform elimination and eliminating these entries, transforming A into the identity, it would take I and transform it into the inverse of A. And so we're doing that same thing here. But instead of having a brand new matrix, we're just going to have a single vector since that's what we're solving for. So as I perform elimination, what's going to end up happening is we're going to take this matrix and transform it into R naught, so our reduced row echelon form. And then he uses D, because this is not going to stay the same. As I go through and apply my process to A and to apply a process to B, we will get a new vector, which he calls D, out of this. And once I get this into reduced row echelon form, like what we saw with the null space, we can start figuring out our answers very, very quickly and solving the system very, very quickly. And so that's what we're going to start walking through and doing with this augmented matrix here. and getting it into this block answer. So if we kind of repeat the process that we've been learning about in this chapter, starting with 3.1, when I'm looking at my rows, I notice that in my first row, I have my first kind of pivot there. I need to zero out underneath, so this one is okay. I need to zero out this entry here, the 3-1 entry. I can zero this entry out by doing row 3 replaced by row 3 minus row 1. So notice I'm essentially multiplying row 1 by 1 and doing that subtraction. As I walk through and do that subtraction, this will create a new block. I'm going to bring it up here just to give it a little bit more space. So first row will stay the same, 1, 3, 0, 2, 1, 6 here. Second row, 0, 0, 1, 4. I was kind of getting ahead of myself when I was writing that in. And now we can start finding the difference. So 1 minus 1 will give you 0. 3 minus 3 will give you 0. 1 minus 0 will give you 1. 6 minus 2 will give me 4. 7 minus 1 will give me 6. And what we can see here, and we see it in the textbook example as well, is that these two rows are completely identical. So if I do row 3 replaced by row 3 minus row 2, this is going to completely zero out that last row, and that's going to create the R naught. Now, it doesn't put our matrix into complete reduced row echelon form. Well, actually it does when we get it because of the 0 above here. So it will actually take us to our finals. Let's go ahead and write that out. I apologize. Typically, we have a couple more steps. The way this problem is written simplifies it a little bit. So I apologize. I was expecting one more step. When I do this subtraction, we will get our final reduced row echelon form. Again, first row stays the same. Second row stays the same. The third row completely zeroes out. Again, this is really, really important because if this row did not zero out, if it was 0, 0, 0, 0, but this was non-zero, then the system wouldn't be solvable. Right? We cannot have 0 equal to something else that's not 0. And that's something we're going to come back to a little bit later. Now you'll notice again, my mistake when I was thinking through is this reduced row echelon form or not, is remember that I need to focus on my pivots. I like to go row by row, which we'll talk more about the row rank and looking at those rows in the next section of this video, 332, if you're following kind of the way that I number things. This pivot has zeros completely underneath, no rows above. This pivot has zeros above and zeros below. So this is reduced row echelon form. And this was the form that when we were solving for the null space was great because the first column is independent, the third column is independent. So my variables x1 and x3 are my independent variables. We can see that x2 and x4 are my free variables. They are my parameters, my free parameters. And x2 and x4 were what contributed to the null space and what allowed me to find the set of vectors that would span the null space. And again, we talked about that in 3.2. So depending on when you watched that, either a week ago or a couple days ago. Now, what I want to do in particular here is to simplify my problem down, and I want to focus on what's referred to as the particular solution. He abbreviates the particular solution as X and then writes particular. I've seen in textbooks, the way that I was essentially instructed was just notating it as XP. So I'm going to refer to it as XP for that particular solution. Now, when we're finding this particular solution, what we're going to do is essentially disregard the free parameters and the free variables. We want to disregard that null space and focus primarily on the independent vectors. So in this case, we're going to zero out x2 and x4. x2 and x4 are both going to be 0. Now, if that happens, then you'll see that this identity chain, essentially the identity matrix where the columns have just been divided across 1 and 3, this tells me the exact solution then for that vector. I can write this out now as x1 is equal to 1. Remember, 0 is x2, x3 is then 6, and x4 is 0. This will provide me the particular solution to my system. That particular solution to the original problem, ax is equal to b, this will solve that. and give me one set of answers. Again, kind of following with the textbook, we see that listed in my solutions. And we could go through and solve this. We could multiply this in and notice because of the zeros and the way that initial matrix is written out, the math will work out. And I'll leave that essentially as an exercise. But when we refer to a particular solution, this is what we're looking for. We're going through and assuming the free variables are 0. We want to find all of the non-zero solutions, the things that won't form 0 as an overall answer. Now, essentially kind of why is that the case? Ultimately, what we're going to do a little bit later, so again, not in this part, but in the next part, is if we're trying to go through and find my solution for x, we'll discuss how this solution is broken up into the particular solution plus, I want to make sure I have the right notation, all of the solutions to the null space, which he calls xn. So all of the solutions to our original system is made up by this sum, which was what I was laughing when I was talking about in addition to earlier. So all of that work that we did in 3.2 and finding those solutions, if I took those answers, which we could identify here, and I add them to the particular solution here, that'll form all possible solutions to our matrix. And recall that when we're solving a matrix and solving really a system of equations, not necessarily just a matrix, there are 3 results that can occur when I'm going through and solving. We can have exactly one solution. The answer is unique. There is only one x particular solution. There is no addition and anything else that can happen. We can get no solution, or we can get infinitely many. Now, when we're looking at this problem here, we can discuss this concept of getting infinitely many because it does not have a full row rank, or because it has full row rank. What it does not have is full column rank. Because I have 2 free parameters, 2 free variables here in x2 and x4, this creates more than just a particular solution. And this is what's going to drive our conversation in the second part of 3.3. It is when we have full column rank, which is going to be kind of our third objective today, where we can essentially have something happen of getting either one solution or no solution at all. And the way that can happen is when we are solving a system that has full column rank, what we're talking about and focusing on is a matrix where every column has a pivot in it. So if this is my matrix A, I'm looking at every single column. That means that when I'm looking at this problem, there could be other rows underneath here. So when I'm discussing rank, in particular column rank, then if I have an n by n matrix, we're letting R, the rank of the matrix, be equal to n. That's kind of the concept. And if R is equal to n, if I have a pivot in every column, then that means there are no free variables. Remember, free variables are only created if there are columns that do not have a pivot in them. And we saw that in the previous example, and that led to essentially there being a null space. Well, if I have a setup like this, or I have a square matrix that again has a pivot in every column, remember that this was invertible, so is this one. And that means then that the null space is only containing the 0 vector, because that's the only solution. There is no free variables. That means that there can be exactly one solution, so only one particular solution, or there is a way to get no solution at all. And in that no solution situation, when these start forming rows of zeros, because these rows would have to be multiples of these above, or in this situation where I get a non-zero pivot, not necessarily in this case, but focusing here, when I get my rows of zeros and I augment my matrix, if I have a 0 here, but then I have a number here, then there is no solution to the system because that is impossible. Right? 0 cannot be equal to 5. And so you'll kind of notice in the textbook, and he kind of highlights this kind of in terms of parentheses, is that there can be one solution or possibly nothing, right? And it's because of when I'm going through and putting into reduced row echelon form, and I get zeros over here, the solution that I have, that vector B, isn't in the column space. And we discussed this effect and getting that result back in Unit 1 and Unit 2. And in particular, I think Unit 1. That's the vector that we're trying to solve for. If that is not in the column space, then there's no combination that could ever get me there, and we see this happen. The null space is still 0, there's still no free variables, but there's no particular solution as well. And so we have to keep an eye out for that. For example, if we look back at that first one that we just solved for, if instead of setting the solution, ax is equal to b, like instead of setting b to be 1, 6, and 7, if instead we looked at it as just b1, b2, and b3, and again we have our original matrix for A, 1, 3, 0, 2, 0, 0, 1, 4, and then 1, let's see what was the underneath, 1, 3, 1, 6. When I go through and I follow the same process that we did to reduce this, 1, 3, 0, 2, 0, 0, 1, 4, b1, b2, I get underneath 0, 0, 0, 0, but here I'm going to have a combination of b3, b2, and b1. He gives it as b3 minus b2 minus b1. And so what can happen in a situation like this is that when I have this row of zeros, if this is not 0, right, if this comes out and is a non-zero number, then that's impossible, and there would be no solution to this problem. There would be no particular solution, xp. Notice there's still solution sets, there's no solution. It cannot be solved. And we would get nothing from this. He gives another example. This is the one that is find the conditions. It's a really similar kind of question. It is when A, for example, has full column rank. So looking at example 1, A is 1, 1, 1, 1, 2, negative 2, 3. B, again, we're just going to assume is B1, B2, and B3. If we go through and we put this in a reduced row echelon form, we'll see the combinations that we need for this to have a particular solution. So I'm going to create my augmented 1, 1, 1, 2, negative 2, 3. B1, B2, B3, like so. I need to eliminate, here's my pivot. I need to zero these out. So I'm going to do row 2 replaced by row 2 minus row 1. I will do row 3 replaced with row 3 plus 2 times row 1. So that'll zero both of these entries out. So I'm going to go through and do that now. So the first row stays the same, 1, 1, augmented with B1. Second row, 1 minus 1, 0. 2 minus 1 is 1. B2 minus B1, quite literally, B2 minus B1. And then for my third row, negative 2 plus 2 is 0. 3 plus 2 is 5. And then I have B3 plus 2B1. B3 plus 2B1. Notice now I have this pivot with zeros all underneath. I move on to the next row. Here's my next non-zero pivot. So I need to zero out the 5 underneath. So I'll do row 3, replace with row 3 minus 5, row 1, or row 2, excuse me. So this will give first row the same, second row the same, third row 0, 0, and then B3 plus 2B1 minus 5 times B2 minus B1. So I'm going to have B3, 2B1 plus 5B1. It's going to be 7B1 minus 5B2. Now, if I go through and put this in reduced row echelon form, notice how this third row here is not affected. Right? So I'm not impacting that last one at all. Oh, did I write this matrix down? Oh, it's -3. Son of a gun. All right, well, or whatever. This will create a new example. So a little bit different from the book. It's vision, right? That's why I wear glasses. If I go through and zero out the center here, so if I do row 1 minus row 2, this will create a 0. B1 minus, so that'll create a B2, or I guess 2B1 minus B2. And then I'll be in reduced row echelon form here. And now, when I'm looking at this setup, I have a particular solution, but I only have a particular solution as long as this is equal to 0. This has to be equal to 0. Because I have 0, 0 here, for there to be a possible solution, this has to be 0. If it is non-zero, then there is no solution to this at all. So I have a particular solution. The null space would be 0. Notice how there is a full column rank. Every column has a pivot. But again, this doesn't guarantee a solution just because that happens. We have to double check and make sure that this works. Now, typically when I'm solving a system of equations, we're not working with the generalization for B. This is checking to see which vectors of B are in that column space. Every vector that's in that column space would have to have this general format in terms of choosing B1, B2, and B3. And that's kind of the interesting effect of trying to solve this in terms of a general vector B here. And so you'll see at the end of this in terms of that one particular solution, and again, his example will be a little bit different because I screwed up with that entry right there, not being negative. That's why when I was looking at this, when I wrote it out, I was like, okay, why am I getting 7 and -5 when I know that wasn't in the textbook? It happens. Is that if you have a full column rank, then there's essentially 3 things that we can glean from that. And he boxes this essentially on page 106. Every matrix A with a full column rank, R is equal to N, has the following 3 properties. 1, all columns of A have a pivot, right? They're all independent, which we've discussed. We see that here. The null space then contains only the 0 vector because there are no free variables. So there are no other vectors in the null space. The answer would just flat out be 0. And then the third, if AX equals B has a solution, it might not, then it only has one solution because there's no extra free variables to create any more answers to work with, right? That extra addition to the particular solution would be 0. And what I'm kind of referring to again for that is X can be written as XP plus XN, right? If that's 0, then there is only one solution or no solutions depending on what we're trying to get to. Again, if that vector is not in the column space like we talked about. So hopefully, barring some of the mistakes in me writing up on the board, we've kind of hit these objectives, and these objectives hopefully make sense and what we can take from it. This idea of solving a system where I'm not setting my AX equal to 0, but AX is equal to another vector, how we can create the augmented matrix, putting that into reduced row echelon form. We can find our particular solution by looking at just the independent columns, letting all free variables be 0. Then we kind of talk about, well, what happens if I have a full column rank? So when, if I have 3 columns, if I have 3 pivots, what that looks like in terms of my solutions, as well as kind of introing what happens if I have full rank is equal to the row rank. So a full row rank is too many R's. Where R is going to be equal to M. And in our first case, we actually saw that happen, where now I have free variables. What type of solutions can we get from that now? What would that look like? And that's what we'll get into in the next part of this video set for 3.3. Let me know if you have any questions.